Hello, I'm Antonio,
And I'm Owen.
and today we're going to be talking about defeating ASLR.
So, what exactly is ASLR? Well, ASLR stands for Address Space Layer Randomization, and it's a computer security technique involved in preventing exploitation of memory corruption vulnerabilities and often acts as the first line of defense for many attacks. And how does it work? Well, ASLR randomly arranges the address space positions of a process, including the base of the executable and the positions of the stack, heap, and libraries, making it much more difficult for attackers to reliably determine where exploitable areas of memory could be.
So, how do we approach defeating ASLR? Traditionally, malicious approaches generally look to abuse vulnerabilities in softwares, such as NOP spray or brute force. However, these are relatively easy to fix and do not reliably work on every system. Even with some level of software vulnerabilities, ASLR has continued to be a staple in software security, as no other method has been discovered that renders ASLR universally insecure. Recently, however, a new method has been discovered that unravels the base of ASLR using the actual hardware of the system. This method is known as the Memory Management Unit cache attack.
So how does a memory management unit cache attack work? Well, in a basic sense, the attack abuses a key function of the memory management unit, or MMU for short. So in order to efficiently execute a program, there has to be a translation between physical and virtual memory, and this has to be fluid and fast for it to be efficient. And traditionally, this has been accomplished through the usage of page tables. A key component of this translation is something known as the translation look-aside buffer, or TLB, which is a buffer in each CPU core that stores any recent translations. The first step in translating a virtual address to a physical address is first, the translation look-aside buffer is searched for the physical address, and if the matching address is found, then it returns the physical address. However, if no match is found, this is known as a TLB miss. The memory management unit performs what is referred to as a page walk and will look up the address mapping in the page table to see if any mapping exists. Also, to improve the performance of these page walks, page tables are cached in fast data caches, similar to how process data is cached for faster access. This means that page tables contain security-sensitive secrets, and knowing these page table cache sets could potentially allow an attacker to de-randomize ASLR.
So the first step is virtual address translation. And as could be seen in this picture, the MMU actually uses the page table for translating an example virtual address. First, the CPU controls a register known as CR3, which will point to the highest level of page table hierarchy, which is level 4. This page table entry has a reference to the level 3 page. And notice that this time the offset is actually 300. Repeating the same operations for page table pages at level 2 and 1, the MMU can then find the corresponding physical page for the example virtual address at the page table entry at level 1 page.
So just a quick overview of the cache architecture. So we have three levels of CPU caches, and caches that are close to the CPU are smaller and faster, and caches further away are slower but can store larger amounts of data. And there are two caches at the first level, L1D and L1I. These are used to cache data and instructions respectively. And the cache at the second level, L2, is a unified cache for both data and instructions. An important property of these caches is their inclusivity, and in a basic sense, this means that while L1 and L2 do not necessarily include each other, the cache at the third level, L3, includes both L1 and L2. And we can exploit this property to ensure that a certain memory location is not cached at any level by making sure that it is not present in L3. So only L3 has to be searched, and L1 and L2 do not necessarily have to be. And current processors partition the caches at each level, and each partition, often referred to as a cache set, can store only a subset of physical memory, and depending on the cache architecture, the physical or virtual address of a memory location decides its cache set.
So now we're going to talk about the basic overview of the exploit. The most difficult part of the exploit is understanding the layout and architecture of the memory mapping, memory management unit, and the CPU cache. Once you understand how these three components work in conjunction, the actual exploit is surprisingly simple. While one cannot read any data from the CPU cache, one can write to the CPU cache. Also, logically, if the write to the cache were to overwrite any part of the page map, then the MMU would have to go and perform a page walk in order to retrieve the correct mapping, and retrieving this correct mapping would in turn take more time. Thus, by recording the amount of time it takes for the CPU to respond, one could accurately determine when the page walks were being performed, and therefore could use that to determine the offset of the ASLR randomization. And now we're going to show a quick demo.
Okay, so for our demo, we're going to be demonstrating a few programs that were used in the creation of this exploit by the researchers at VSEC. And while they have released a portion of their code base, and this includes a few programs necessary for creating the exploit, unfortunately, the researchers have deemed the exploit potentially too major to fully release, and thus do not include the actual JavaScript that's needed to completely de-randomize ASLR. So we're unable to demonstrate a full ASLR cache exploit where we actually completely break ASLR, but we will demo the programs that are needed to create the full exploit. And the first program that we will show is the ANC program, and the ANC relies on the fact that page table lookups by the MMU are stored in the last level cache, and they do this in order to speed up the next required translation. And by flushing parts of the last level cache and timing the page table lookups, ANC identifies which parts of the last level cache store the page tables. And on top of flushing the last level cache, ANC also needs to flush the translation look-aside buffer and also the page table caches. Since the information on the size of the translation look-aside buffer and the last level cache is available, the ANC tag can be used to reverse engineer properties of the page table caches that are of interest to the attackers, like internal architecture and size, and these could be used to completely break ASLR. All right, so for the ANC program, normally one can simply run it just by typing out this, and you don't need to specify any extra options. Our specific CPU, this does not work. We get a failure and 2 slot errors. And this is because while Intel Ivy Bridge and older microarchitectures than this do implement a translation cache for page table entries, there is either no translation look-aside buffer to cache huge, like 1 GB pages, or the existence of it simply not reported by CPU ID. And the CPU we tested this on does contain an older than Ivy Bridge microarchitecture, so we're going to have to specify the amount of entries. So that will look like and all right, this should be the correct command. And yes, as you can see, now we get 0 failures and 0 slot errors. And this is completed now, so we've retrieved quite a bit of information on the architecture, and this also allows us to run a script that they provided us with, and that will create a graph with cache line offset in the page table on the x-axis and consecutive pages on the y-axis, and you run that via. Okay, so we had some technical difficulties with running the script on Antonio's machine, so we've now switched to my machine, and we are going to begin at the point we left off before. As you can see, I've already run the ANC program, so now I'm ready to run the script that's going to plot the cache line offset in a page table versus the consecutive pages. And you do this just by this simple command right here. Yes, and as you can see, we have the mmugram.pdf right there. Open this up. And it
takes a second to load, but we should see the graph here in a second.
So yes, as you can see, it provides us with all 4 levels, and on each level we have the cache line offset in the page table and graphed against the consecutive pages. And you can see it gives you kind of a nice overview of each level.
So yeah, now we're going to talk about mitigations. So there are 2 key ways. The first one is artificial delays. Since determining where the page maps are depends on the timing of writing over the CPU cache, a defense could be to include artificial delays in fooling the malware to believe that it has found the page map location when it really hasn't. Another way is isolated cache. By caching page table entries into a separate cache rather than a data cache can mitigate the attack. However, having a separate cache just for page tables is quite expensive for the hardware, and adopting such solution is kind of defeating the purpose of ASLR, which is to provide a low-cost first line of defense. So the importance of ASLR is that it exploits the hardware imperfections rather than the software. And there is really no easy fix to this exploit because it's relatively new and it's really hard to fix. So Given that, the coming years, there is definitely going to be different approaches other than ASLR to act as the first line of defense for program security.